We started with SVM, right? Support vector machine. It is like logistic regression only, but the main difference between logistic regression and SVM is SVM takes the help of support vectors to do the decision boundary. The advantage of taking support vectors to do the decision boundary is edge cases will be covered very you know uh, very efficiently. So if the algorithm chooses these two as decision boundaries and does the support vectors and does the decision boundary, when in a test set if some records fall somewhere in this area, right, it would have been predicted wrong because of the decision, the margin, right, margin between two support vectors is small. So it always chooses the um, support vectors in such a way that the margin is large. Okay, large margin is the basis to select the support vectors. Based on support vectors, it will do a decision boundary parallelly to the support vectors. So it will choose always this one. So I just try to show the difference between different support vectors. When the support vectors are changing, the angle of the decision boundary is changing. Depending on the angle, the predictions will be more accurate. Okay. So basically in logistic regression also, decision score is the distance between the support, the decision boundary and the data point. So when you take a large margin between two support vectors, that means all the other points will anyway are far from the decision boundary, right? So how far it is, that better the prediction is. That is achieved by taking the large margin between the support vectors. The closest data points are farther. When you look at different these three different models are the way, if it takes these two or this one, the closest data points are themselves far from the decision boundary. That means this is going to be more clear prediction. If the data point is very close to the line, right, then the decision score is going to be less, very close to zero. Okay, so if it is far, it is a bigger number. It may be a negative number or a positive number. That was achieved by taking the support vectors. Okay, large margin in a way helps to get the decision score high for all the data points. In another way, if we have to explain. Okay, and there is a hard margin classifier and large margin, soft margin classifier. Theoretically, right? Theoretically, hard margin classifier, there is no implementation for this. Hard margin classifier cannot do a model for this kind of data. No, it should be clear. Data should always be clear. One class of record should fall on one side of the decision boundary. If not, right, it's not going to do. So linear SVM we are talking about, right? Linear SVM. If you take non-linear SVM, today we are going to talk about it. It'll actually do a hard margin classifier also. It will do like that. Okay, it will do like a curve like that. Okay.
Sir, it will throw any error, or like how do you know that like it will not creating the decision boundary if it is a odd margin classifier?
It'll not work. The predictions will not work. When you try to predict, right, it will give wrong predictions.
So how do you know that sir it's wrong prediction? It will give
Test set,
some
right?
number.
On the test set or train set, we can predict, right? We can, when we predict it is giving very less accuracy, means it is not working well.
Okay, that way we need to understand. Okay.
Yeah, only numbers. Visually, we cannot understand. So yeah, I think your question is, can we visually see, right?
Yeah, usually say
Yeah.
means like it will give any exception or any like kind of
No, it will
message.
not give any exception. It will not work. The model will take some coefficients, the parameters, right, equation W's, and
Hmm.
they will not work. But you know, in a linear SVM, when you are trying to do a model, right, it will always try to fit it well, you know, in a linear way or non-linear way. We'll see today. You know, I'll explain you how
Okay, sir.
to do a non-linear decision boundary with SVM. When you do non-linear SVM, right, you can do hard margin classifier. So hard margin classifier means it is trying to put all the different class data points into one side of the model. Okay, it is very difficult. Very rarely it will happen. If you use the existing, you know, implementation and try to do a hard margin classifier, it will very rarely happen in real time because the algorithm, you know, maybe it will overfit. We can say it will overfit. Right? If you see these diagrams, yeah, you see these diagrams, right? We almost all tried to, you know, see this, all the data points fell, all the blue points fell was a side and red dots fell another side, right? This is hard margin classifier. Okay, so using soft margin classifier you can do a hard margin classifier, but it'll data is like that, so it happened, but it is very overfitted, right? On trained test set, right, it may not work. If one data point, maybe 10 data points fell here on the test set, if you pass 11 records and 10 fell on the line on the wrong side of the decision boundary, model, you know, looks like it is not working. Right? Got it? Got it, right? Narayan.
Yes, sir. Yes, sir. Yes, sir.
So that is hard margin classifier. You can do using soft margin classifier, but doing hard margin classifier is not, no, not suggestible. Indeed, it may not happen all the time. Yeah, 99% of the time it may not happen. We are taking the logistic regression class function and logistic regression algorithm to analyze and understand SVM because that's the easiest way. Okay, the math is very complex, so now we took the logistic regressions cost function and looking at the SVM's cost function, they both look similar. Okay, the cost function here is hinge loss, right? Will be, you know, a gap between the negative and positive, -1 and 1. You know, um, in log loss or the logistic regression, we had that zero point 0.5 as threshold, exactly less than 0.5 or greater than or equal to 0.5. We are distinguishing classes, but here -1 and 1 we'll say, right, to have that no decision boundary, right, gap, the decision boundary, sorry, the large margin gap. Okay, so um, when you look at C, right, it is a inverse of lambda. So when you increase lambda in logistic regression, the overfitting will reduce. If you decrease lambda, overfitting will increase, or overfitting will come to a place where it was originally. Okay. In C, right, with C, if you increase C, overfitting will increase. If you decrease C, overfitting will decrease, directly proportional to overfitting, this C hyperparameter. So that's what we have seen here. C is equal to 1, margin is high, and no, there is a violation. Right, on the train set also it's violating. This is a train set, picture of a train set. Right? It is violating. One data point fell on the wrong side. So prediction is going to be a little weaker. Right? But on the test set it will work well because the margin is high. Right? Margin is high. The angle also changed a little bit. If you carefully look at it, this is no, this is steep. This is a little slant. Right? When you're increasing C, it is actually becoming steeper. Here, because data is like that, it is becoming steeper. Right? Depending on data, the line will change. Okay, so on the wrong side, we are having one data point. That is okay because on test set, if it works, if it works well, right? If test set is also like this, right? Maybe C is equal to 100 will work well on the train set and test set also. Just to show you that it becomes overfitted. Overfitted means exactly trying to, you know, fit all the data on the right side of the, so this is like hard margin classifier. Okay? So that is one example. And then we have seen the scaling importance. If you, when we don't do scaling and try to do the decision boundary, two data points fell on the wrong side. Okay, and it was actually kind of hard margin classifier. It is looking like a hard margin classifier. But there are two data points fell on the wrong side. We shouldn't be saying that, but it's like it's looking like, you know, a bit overfitted, or the line is very congested. But when we did the scaling and tried to do a model again, there is a large margin. So scaling is very important for SVM. Feature scaling is very important. So we have taken this iris data set and tried to build a SVM model. Okay, good. Tried to build a SVM model. So we built a SVM model, right? So it is very simple, right? We have taken a clean data set and just splitted the data and then did the standard scaling and applied a linear SVC. Okay, using linear SVC, we can do a nonlinear decision boundary also. I'll explain that in a moment. So we built a model and then we looked at the confusion matrix separation recall scores on the test set. It is working good because the data set is very simple and straightforward. It is good. It is working good. And SVM cannot work with huge volumes of data. That point we should remember. Okay. The other problem with SVM, right? If you have a non-linear decision boundary, I think one image is missing here. Give me 1 second. Yeah, this is the, so no, this is the image I am looking at. So if your data is like this, right? So X and Y are, you know, we have only X, only one variable we have. Okay, one input variable, and output is the color. Okay, so these black dots belong to one class, and red dots belong to another class. If you have to do a decision boundary, you may have to do a decision boundary here or here. Right? In any angle you do, it doesn't matter. Two data, you know, if you do a decision boundary here, these four are falling on the wrong side. If you do a decision boundary here, right, these two are falling on the wrong side. So now the only way you should be doing a decision boundary is like that. Right? Parabola. You should be doing a parabola. But you know, in linear regression and polynomial regression, we actually looked at converting the line into a polynomial curve by adding polynomial terms. Do you remember when we had to do a uh, nonlinear fitting through the data in a linear polynomial regression? What we did? Do you remember?
Adding degrees.
Adding polynomial terms actually made the line to a curve, and we fitted it, right? But in this classification problem, right? We will not say we are adding, you know, in SVM basically we will not say we are adding polynomial terms to make the line curvy. When we add the polynomial term to the data, right, it will actually become curvy. So it's a other way around. We'll talk, right? So I have no x1, sorry, x minus 5, minus 4, minus 2. So the data is like this. Let me try to show you the data set. Let me show you the data set. So there is X and there is Y. Okay. So let me take. There is an X and there is Y. So I am actually trying to create data set for this particular graph. And there is -5, -4, -2, -1, 0.5, 3, 4, 6, 7. And this is black, black, red, 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 black, black, black. Right, color is the class. This is how it is. Okay, one more black. 6 and 7, 3, 4, 0.5, 3, 4, 6, 7, 3, 4.
3 is not red.
Okay. But here only 3 came.
Yeah, -2, -1.5.
-2, -1, 0.
Yeah, 0.
0 is also red. Okay, so this is how the data is. Okay, and if you have to do a decision boundary, either you have to do it here or here. In either case, these two or these, these four are actually being misclassified. Right? So what we do is when we add a new term, when we add a new term here, right, x square, what happens? This becomes 25. This becomes 16. 4, 1, 0, 0.025, right? 9, 16, 36, 49. Right? That's how the data set became. Now, right, from between x and x square, right, we are doing a graph. So the dots now actually rows, right? See, for -5 it is 25. For 4 it is -4 it is 16. Right? Either it is negative number or positive number. The y is going to be positive. Okay. Either it is the x square is going to be positive, whether x is negative or positive. So now it is neatly represented. Now you can do a decision boundary like that. So in SVM, when you are using a linear model to do linear SVM to do a non-linear decision boundary, you should be raising the data to additional polynomial terms so that the data set becomes non-linear and you do a linear decision boundary. So total SVM talks about the non-linear decision boundary like this only. It will not talk like you are actually trying to create a curvy line through the data. Okay, in logistic regression I showed you, right? 1 by 1 plus e power minus x square minus minus x1 square minus x2 square is a circle, right? So when data was like this, I don't know whether you remember that diagram. When data was like this, right? I actually did a nonlinear decision boundary, a circle like that, right? I said that the equation is going to be 1 by 1 plus e power minus x1 square minus x2 square, right? If you think this is x1, this is x2, two input variables, and the output is a color, right? If you think the data set like that, right? I said that like this, right? We are doing a nonlinear decision boundary, I said. Basically, we are not doing a nonlinear decision boundary. There also, we are raising the data to to another dimension. Okay, we are raising the data to another dimension. We're adding the polynomial term, and then we're doing a linear decision boundary only. SVC and linear SVC, two algorithms are there, two models are there, two classes are there. We are using linear SVC now, right? We'll use SVC, today itself. where we can actually implement kernel trick also, which will actually raise the data to another dimension. Okay, it's a more complex way of raising the data to another dimension without uh, uh, increasing or reduce by reducing the number of columns. Okay, we'll talk about it later. This point you got it. When you add polynomial term, the data set is becoming a little different, and then we are doing a linear decision boundary to the data. Got it? Any questions? Okay. So if you I have taken one make moons a data set. It looks like moons, right? So it's a scikit-learn data set, experimental data set, and then I use some code to plot it. But in real time, right, we will not be able to plot all the data sets. The theory and the classes looks colorful, but we cannot make everything colorful in real time. Okay, so for understanding purposes, I've shown it here. If you have to do a decision boundary, you have to do like that. Okay, so if you add polynomial terms to the data set, at one point in time, they'll become like this, where you can do a decision boundary. It may be a multi-dimensional space. So here only 2 dimensions we were able to see, right? We had only one input feature. I added second input feature, it became 2 dimensional, and then I showed you a line here, and then kind of was able to. This is actually generated, using the data. We built a model and generated it. Okay, so we can. I was able to show it, but on a multi-dimensional, right? If you here, how many variables are there in this data set? Yeah, 2 variables are there, 2 input variables and 2 colors. So yeah, the classes are 2 colors, green and blue. Okay, and I am using polynomial features again to raise the data set to a degree, and standard scaling and linear SVC. So first we should be applying polynomial scaling. First we should not do standard scaling. If you do standard scaling first and then apply polynomial terms, the small numbers, right, 0.5 will become 0.025. If you raise it to fourth degree, right, even lower it will become, right? So this is the pipeline, right? So the polynomial features, standard scaling, and linear SVC. And then I have taken param grid, where I am taking the degrees for this polynomial feature from 1 to 20. That means 19, right? From 1 to 19 it will take. Okay. And then the C hyperparameter 1 to 10. So it's going to do 190 models. When you do grid set CV, where is it? Yeah, I'll show. So when you do grid set CV, it will actually do 190 models, and if CV is 10, it's going to do 1900 models. Do you agree? Any questions there on that statement?
Come again, the statement.
So, so if you look at this param grid, right? Degree, right? Degree hyperparameter, right?
Yes, yes.
C hyperparameters also that I showed you. When you are increasing C, the orbiting will increase. When you decrease C, orbiting will decrease. So to find out the best model or best hyperparameters, I have taken these two parameters into the param grid.
Yes.
When I do grid set CV, I'm not sure. I'm not doing grid set CV randomized. I'm doing it here. When I do grid set CV with this pipeline and this param grid, how many models it will create? I said it is going to create 190 models here, and if I take CV is equal to 10, it is going to do 1900 models in total to decide which hyperparameters it will best fit, right?
Oh, got it.
So it is going to be very tedious process, right? It will take a lot of time if you use grid set CV. So there is another way, randomized grid set CV, which will actually randomly take 10 combinations. However many combinations you give, it doesn't matter. By default, it takes 10 combinations. Let me show you the API. It is, I never used it, but there is an option, right? So it will actually randomly pick 10, as a human being, right? What you will do, you will actually you'll play with the model for some time and find out a range, and then you give that range into the param grid, right? And then you try to do randomized HCV. That way it will actually try to pick 10 random combinations, right? So randomly it will pick 2 here, randomly it will pick maybe 5 here and try to build a model. Again randomly it will pick 3, 8, build a model. Again 2, maybe 3, build a model. Like that it will actually pick, instead of doing 190 models, it will do only 10 models with CV 10. So it's going to be 100 models only. By default, the number of models it's going to pick is 10. You can increase this. Okay, if you want more random combinations should be taken, random pairs should be taken, then you can raise it. N letters if you raise, it's going to take more combinations. So randomizer set CV is like grid set CV only, but it takes only 10 combinations. Grid set CV will take all 190 combinations. Got it? Got the difference between randomized and this one? And builds the model and finds out of all those 10 combinations which one is best. Got it? Any questions? So randomized set CV is useful when you are already almost close. When you played with the model and found some degree and some C are working, right? Some degree and some C are working. You already know that almost 90% on train set, 90% on test set you are getting already. Maybe a little bit of difference is there. Then you can actually play with randomized set CV. Okay. So if you are not sure, right, you should play with it more and then maybe try to use grid set CV, which is going to be more accurate. Okay. So here we found the randomized set CV, we found best parameters and best estimator. See, these best parameters are 1C and 16-degree polynomial is the best model. So I have taken this code, right? Whatever this graph code from Alan Geron's book. Okay, so you look at the code, you look at the graph generation code here. It will be you'll be able to understand, right? So how to do triangles, how to do boxes, all that is there. In API anyway, it's going to be there. So I have taken. So I have taken grid set CV also. It will take time to execute grid set CV, right? And then try to do a plot. Okay. So when you do grid set CV, it's going to do 1900 models and it will find the best hyperparameters. When we did grid set CV, the polynomial degree 3 and C2. And when I did randomized set CV, C1 and degree 16. There is a lot of difference between the outcome, the parameters found by randomized and normal grid sets. So normal grid sets is better, even if it takes time, it is better. If your data is too huge and you don't have that much time, then doing randomized set CV is good. Okay.
Oh, but the variation is too.
Yeah, too high, too high.
I don't think that is reliable, right?
That is not reliable. Only when you already know the hyperparameters, right? Closed hyperparameters. If you already know, right, 2 has a degree and C maybe 1, maybe you can give that range between maybe 1 to 3 or 1 to 4 as the degree, and 1 to 3 as the C, and take maybe 100 there, 100 here, then try to do a randomized set CV with maybe 100 iterations, something like that. It depends, right? You already know the range, closest, the best hyperparameter range, then randomized is good.
Okay.
Variation is going to be less. Whether you use grid sets or randomized sets, the finding is not going to be that different if you already know the ranges. Anyway, you are searching in the close range, right? So here the range was very high, right? From 1 to 20 I gave, and like that, right? 1 to 20 and 1 to 10. This may not be that big, but this is very big range, right? So when the range is too high, you should not be using randomized set C. Let's set CV. When range is low, whether you use randomized or grid set, you will find almost close hyperparameters. Okay. The time will be less, less time will be used. Instead of we trying to randomly search in the known range, we are trying to make the scikit-learn search. Okay. So the problem, right? What is the problem, right? If you have nonlinear data also, we are able to do a nonlinear decision boundary with linear SVC. But the problem is the polynomial degree cannot handle very complex data sets, because if the complexity is more, the polynomial terms are going to be more. So the data set will become very huge. We call that as dimensionality. Data set's dimensionality will increase. Number of columns will increase. Okay. So the one solution is deep learning. Without, one solution is to, on a huge volume of data, huge number of columns, trying to build a model is deep learning. Deep learning can solve that problem. That is one. The other way is to reduce the dimensionality. If there are too many columns coming in, right, we can reduce the dimensionality. So the trick called as kernel trick will help us reduce the dimensionality. So here I've taken third degree polynomial, that is okay. But if I say, in the data set, if you have 10 columns and say 10th degree polynomial, it is going to be n plus d factorial by n factorial into d factorial, right? I was trying to remember that. So 110, 20, 20 factorial by 10 factorial into 10 factorial. So it's going to be almost yeah, it's going to be big number, right? There are going to be many columns there. So then if you do, if you have to build a model, the memory is not going to be sufficient. So the same problem, right? With the polynomial regression, what you have encountered, same problem will come here. When data set is huge, the dimensionality is high, there is another way. You can reduce the dimensionality by losing less amount of uh, essence in the data. That can be done with kernel trick. So if you are good with whatever we have known so far, I'll go into the kernel trick. So there is a math, there is a little bit of math there, you need to understand. Are we good?
So we are actually increasing the dimensionality to fit for the nonlinear data.
Yeah, to fit a straight
So
line through a nonlinear data.
again, we are saying we will decrease the dimensionality.
No, dimensionality will not decrease. Reduce the dimensionality. Reducing dimensionality is not decreasing polynomial degrees. We'll actually mix and match and try to create a new data set which will actually have the essence of the data, but reduce the dimensionality. Number of columns will reduce. At the same time, it will have the essence of the data. A polynomial essence will be captured, or whatever, no, whatever the pattern in the data will be captured. Yeah, that's a good question. Reducing dimensionality, are you going to, take out some polynomials? No. Polynomial terms? No. We are not. So this is the concept we have seen, right? So when you raise the data to higher degree polynomials, it is allowing us to do a linear decision boundary. So in kernel trick also we will do that. No, we are raising the polynomial degree or adding polynomial terms to make the data set non-linear so that we can do a decision boundary. There is a mathematical trick called as kernel trick which will also try to do the same. So if your data is like this, right? So x1 and x2 are there. We added a new term to the data, the kernel trick. We should not be saying it is a term, right? When you actually do apply the kernel trick, it will actually kind of add a third dimension. If you have two input variables, it will add third dimension. If you have 10 variables, it will add 11th dimension. If you have 100 variables, it will add 101th dimension, right? That dimension will try to raise the data in such a way that you can do a plane, hyperplane between the data points. Same concept, okay, but mathematically it is a little interesting I would say. Okay, kernel is a mathematical trick that derives new features based on proximity measure for each row and all landmarks. So this is the key point you need to remember. Okay. Only this point I am going to explain now. Okay, so derives new features based on proximity measure for each row to all landmarks. Proximity measure. What is proximity measure? What is proximity measure in English?
How close it is.
How close it is, right? For each row. Till here you are clear, right? Row you know, right? In the data, row, right? All landmarks you don't know, right? Landmarks are nothing but all rows. Okay. So same data, right? If you take first row, you take distance between first row and second row, first row and third row, first row and mth row. Okay. Kernel trick is a mathematical trick, derives new features, right? New features based out of the distances between the first row and first row and second row, first row and third row, and first row and nth row. Again, it takes second row, does the same thing. First row, second row and first row, second row and second row, second row and third row. Like it is like, we five are there in a room, right? We wanted to look at differences between, right? Each person will have his own or her own attributes. If you are, genome, take the DNA sequence of each person. It's going to have 1 million columns, right? It is going to have 1 million columns. We are 5 people. There are 1 million columns, right? So now if you have to build a model, it's going to be complex because 1 million columns are there when you do SVM or any other polynomial. It's going to raise the dimensionality and all. If you kind of took differences between or distances between each person's DNA and other person's DNA, you will get one number only. Yeah, let me show you that. So this is the example. So there are 5 people. Each person has got 1 million columns, right? This is a hypothetical example, right? Hypothetical example. You cannot decide, whether a person is good or bad by looking at the DNA, right? The education, the profession we are in, all doesn't matter whether we are good or bad. Similarly, the physical attribute, right? The DNAs are also physical attributes. They cannot actually measure good or bad, right? But I created some scenario to explain here. So if you have to take a person's DNA, need to predict whether he or she is good or bad, we have to build a model, right? We have taken some sequence of 5 people and we said good, bad, good, like that. We label the data. Okay, now we need to build a model. If you take the same data and try to build a model, right, it's going to be difficult. So what we did is we took differences between each person and the other people as the data set. See this here? The distance between 1 and 1, distance between 1 and 2, distance between 1 and 3, distance between 1 and 4, distance between 1 and 5. So out of 1 million columns, I derived 5 values. Right? 1 million columns and 5 rows, I derived 5 values. Okay. For the second row also, see, for the second person also, I took the difference between distance between, how do you calculate distance? Between two rows? Euclidean distance or
Euclidean.
Manhattan distance, right? So yeah, good. So distance between the second person and first person, second person and second person, right? If you are just calculating Euclidean distance, what is going to be the value here on the diagonal? If you are using
0.
0, right? If you are using Euclidean distance, right? Suppose that these are numbers, you converted all these numbers to 26 numbers, right? A, T, G, right? Only 26 numbers will be there. So you converted all the letters into numbers, right? Now you are calculating distance between 1 and 1, 0, 2 and 2, 0, 3 and 3, 0, 4 and 4, 0, 5 and 5, 0. If the distance is too high, what that means? If distance is 0, what that means? For a record, for any record, right? For any cell, suppose that in this cell you got 0, and you will get 0 on the diagonal. We know because it is distance between the same person. But in a particular cell you got 0. What that means?
Those two are identical.
Those two are identical, right? The distance between those two data points is 0. That means they are not different. The data points are not different. So you are actually capturing the difference between two data points. Is that an essence of the data in a way? Are we capturing essence here? If if two data points I've taken distance and I've got a big number. I've got two data points difference. I got 0. I calculate difference between two data points. I got a big number. Right? That means these two are completely different. These two are kind of same, right? Like that, we are actually kind of capturing the million column data's essence into 5 by 5 matrix, because there are 5 rows. If you have 100 rows, you will have 100 by 100 matrix. If you have 1000 rows, you will have 1000 by 1000 matrix. Right? From 5 by 1 million data set, I reduced the data set to 5 by 5 by capturing the essence as the cell value. Now if I build a model, right, the model will, it actually captured uh, distance measure as the essence from the data set, and we are trying to use the distance measure to build a model. There is already some intelligence in the data set, in the input space, right? Using that intelligence, when we build a model, right, it will work, right? It will work, even may not be like the whole data set, but almost all like whole data set. Do you agree? Do you agree? The kernel trick is based on this concept. Do you agree? Any questions? Do you understand? First thing.
Sir, did not understand the reduction actually. So 1 million records, how it is?
See, simple, right? If you calculate Euclidean distance between one record and another record, what you'll get? What is the outcome of a Euclidean
One
distance?
number.
One number, right? So I took the first record and the first record, calculated Euclidean distance, 0 I got. First record and second record, one more number. Third record, first record, third record, first record, 4, first 2, 5. So between first record and all the other records, I reduced it to 5 numbers. Is that clear? No?
Not sure. I am only the one person and I'm not getting. So there are 1 million records, right? When you compare it.
Yeah. 1 million columns there are, 5 rows.
Okay, there are only 5 rows and 1 million
1
columns.
million columns. Your idea, right? You are actually thinking like that. No. Only 5 rows and 1 million columns. DNA will have too many values, right? Human DNA. Any species DNA, I don't know whether you know it or not. If you take a human being's DNA, it is like piling papers in 10 rooms, right? That much you can write DNA sequence A T G T G like that, right? For 10 rooms filled up with papers, you can write that big it's going to be.
Mm-hmm.
Okay, so 1 million columns. I'm just saying 1 million columns, maybe even more than that.
Yes, go ahead.
Now
I
you
was
got it.
thinking a different way. I
Yeah.
was thinking 1 million rows and.
No, only 5 people. I have taken only 5 people. For each person, I have taken the DNA and then calculating the distances and trying to, I'm trying to kind of capture the intelligence into input space itself. Before even building the model, input space itself has got some, intelligence there. Now I build a model. So this is the basis for the kernel trick, right? Any questions here? Okay. So if you take Euclidean distance as a measure, right, what is happening? Between the person and person itself, you are getting 0. Right? So if you can produce somehow, right, somehow if you can produce 1 in the diagonal space, and then if the distance is too high, a number close to 0, if the distance is they are very close to each other, a number 1, that will be better. Okay, as a representation, right, as an intelligent representation of my input space, instead of showing zeros on the diagonals, show ones. If some data points are too far, show 0 and close to 0 rather than 1. So I am actually flipping that. To understand the trick, we understood with the Euclidean distance. Now we will be looking at actual kernel function. One function I am going to show you, radial bias function, we call it as. Okay. So this is one function. You can have any n number of functions, polynomial functions, any number of functions you can have. Okay. When you apply kernel trick, even if it is polynomial degree, the data set will not become more than m by m. See this here? I have taken 5 rows. The input space became 5 by 5. If you take 10 rows, it will become 10 by 10. If you take 100 rows, it will become 100 by 100. Do you agree? Do you agree? When you apply kernel trick.
Yes.
Understood, right? That's a key point there. Okay? That's a very important point, what I actually spoke, right? How many number of rows you have? That many, that much, row by row matrix, a square matrix, it will become the input space. It doesn't matter how many columns you have. If you have less number of columns, right? Applying kernel trick is not that useful. I'll highlight that point in a moment. Okay.
If number of rows is very huge, then it doesn't work, correct, sir?
It's not. It doesn't make sense, sir. It works, but it doesn't make sense. I'll actually show one example also.
Sure.
So basically, SVM is a very intelligent, very theoretically very intelligent, algorithm. When there was no deep learning, SVM was very famous. When you have deep learning, right? I don't think SVM is is anyway useful now. Okay, that useful now. So radial bias function we call it as. What is that function? This is the function. E power Euclidean distance square, right? Minus Euclidean distance square divided by 2 into sigma square. This sigma is not a standard deviation, right? This is just a number. Okay, this is just a number, a hyperparameter we call it as. Okay, so here, while explaining, I said the distance measure is Euclidean distance only. When I took Euclidean distance, I've got the closest data points 0, farthest ones a big number. Instead of that, if you can get some, you know, uh, some number between 0 and 1, right? This radial bias function will give you a number between 0 and 1. 1 being very close, 0 being very far. We are actually standardizing the essence also. We are converting 5 by 1 million data set into 5 by 5. On top of it, we are standardizing data. We are actually quantifying. The data knows, right, whether it is too strong or too weak. Whether the relationship between that record and the all other records. If you have, if you have a record with numbers which are very close to 1 in all the cells, that means that record is very strongly related to all the other records. If a record is having, numbers which are very close to 0, all the numbers in the row very close to 0, they are all, that record is very weakly related to other, other data points. Maybe the weakly related data, the data points are records, maybe bad ones. Strongly related ones may be good ones. That pattern is already captured. The intelligence is already there in the input space. Now you build a model. Model makes sense easily. The pattern recognition becomes easy. Okay. So these kernel functions, right, will actually standardize the data. They actually bring data to a certain kind of pattern. That way the algorithm will be able to easily identify. Okay. So how this radial bias function works? If you see this, right, I have, if you look at this function, I am using this function to calculate the distance measure. Here I said Euclidean distance. Now I am using this function. When I use this function, right, we call it as so I'll talk about that later. So our RBF function, right? RBF function. So see this RBF function output. The distance between the person and person itself, right? So e power minus of person minus person. When I say person and person, what is person here? What is person? Is that a matrix or a vector or a number?
Vector.
Distance between two people.
It's a vector, sir. It's a vector. Person, only person means it's a row, right?
It's a row.
This row represents a person. This row represents a person, right? So here, person minus person means norm of a person minus person, right? Norm, what is norm? The two lines, norm is the distance between two vectors, or the length of a vector, sorry, length of a vector. So when you subtract one from the other, right, and then do norm, it is Euclidean distance only. This norm, right, norm of a vector is a Euclidean norm of a distance between two vectors is a Euclidean distance only. You are applying square to avoid the square root, right? Euclidean distance is square root of x1 minus p square, x1 minus p1 square plus x2 minus p2 square plus x3 minus p3 square, like, and so on, xn minus pn square, right? N columns. Okay, so you are taking distance, right? It is 0. Same person and same person, if you calculate Euclidean distance, it is 0. 0 square divided by 2 sigma square is 0. E power 0 is 1. Okay, so between the person and person, it is producing 1. That means when two records are very close, you will get a number that is close to 1. Okay, if two records are very far, what will happen when they are too far? Suppose that take this and think that the first person and second person are too far. What will happen? In the numerator, you will get a big number, right? And this e power 1 by person minus person Euclidean square is going to be a big number. Do you agree? Am I going fast? If two persons are very far, the Euclidean distance between two vectors, is it going to be big number or small number?
Big number, sir. They are far, it's a big number.
Yeah. When you calculate Euclidean distance, when they are far, it's a big number, right? So when it is a big number, e power minus big number, right? I'll take maybe 100, maybe 1000, right? Divided by, suppose that you took sigma is equal to 1, right? Sigma is equal to 1, or maybe sigma is equal to 1 by 2, 0.5 you take. And what will become? Square it is, okay. So I'm trying to make it 1, right? 2 sigma square 1, we take 2 sigma square is equal to 1, right? E power minus 1000, it's equal to 1 by e power 1000. Is this number close to 0? Is this number close to 0?
Oh, yes, sir.
Right? When two people, right, two vectors are far from each other, two rows are far from each other, then the RBF function will generate a number close to 0. When they are close to each other, it will generate a number close to 1. So the function actually helps you extract the essence and keep it in the cells. Got it? Got it?
How is rho calculated, sir?
Each row?
No, the standard deviation in the denominator.
No, it is not standard deviation, sir. The sigma is not standard deviation. It's a number. It's a hyperparameter. I'll talk about that. It's not standard deviation.
Okay.
Those guys actually notation they took it like that. Everywhere it's going to be like that only. Sigma only.
Okay.
Sigma and gamma they are going to use. I'll talk about that. Once we understand this concept, right? Good. Any questions so far? How RBF function is generating the data or converting the input data in such a way that it extracts the essence. What is the essence? A strong relationship other records or not. This person is strongly related to whoever all, right? This person whoever is weakly related, all those numbers are going to be 0. So the similar people will have similar numbers in the cells. Similar people will have similar numbers in the cells. Do you agree? Right? And similar people will have same, similar y value. The class is going to be same. That way, data is intelligent now. We induce intelligence by using RBF kernel. Got it? Got it, right? I'm moving on. Okay, so that is, the RBF kernel, produces a number between 0 and 1. The closest to the point 1, closest points will get a number close to 1. Farthest points get a number close to 0. So I explained that. Okay. So you can take is a squared Euclidean distance between x and the landmark. What is landmark here? When you take this x as the record, this first record as the one you are trying to calculate Euclidean distances, then all this record and all the other records become landmarks. So first record minus landmark, first record minus landmark, first record minus landmark, first record minus landmark, first record minus landmark. So landmark 1, landmark 2, landmark 3, landmark 4, landmark 5. All the other data points are called as landmarks. That's it, simple. Got it? What is landmark? You got it? What is landmark? You got it?
Other data points, sir.
Other data points, including this data point also. Right here, this first data point is a landmark. Here, second data point is a landmark. Here, third data point is a landmark. Right? So itself is also a landmark. Other data points and itself is also a landmark. All records are landmarks. Current data point is x. Okay, x minus L. The Euclidean distance. Sigma is a free parameter. It's not a the standard deviation. We'll play with that. And in the scikit-learn, right, it is represented as gamma. Gamma is equal to 1 by 2 sigma square. Notation, that's it. Okay? 2 sigmas. Somebody may use sigma, somebody may use gamma. But how exactly it affects, I'll show you. It will actually be useful in playing with high, the overfitting and underfitting. Okay. So this kernel trick, I tried my level best. Okay, but I think I make lots of sense. But if you look at the internet, right, everybody will confuse you with the kernel trick. It's a very simple trick. It's a very simple trick. Okay. Now let us see how exactly this gamma or the gamma or the sigma will help in reducing overfitting or increasing overfitting. So here, suppose that there is an x and there is an L, and the Euclidean distance between the numerator is 10. Okay, and gamma is 1. If you take gamma is equal to 1, this is a one hyperparameter, right? So if you take gamma is equal to 1, what will happen? E power minus 1 into 10 square. It's going to be 1 by e power 100. Okay. If you take gamma is equal to 0.5, it will become e power minus 5.5 into 100, right? Whatever. It's going to be 1 by e power 50. Okay. So if you take gamma is equal to 1, right? Distance between same x and same L showed it as far. Do you agree? When you took gamma is equal to 1, it showed it as far when compared to gamma is equal to 0.5. When you took gamma is equal to 0.5, right, it showed that the distance between those two data points is close. Do you agree by looking at these two numbers? Do you understand? 1 by e power 100 and 1 by e power 50?
Yes.
Right? Using gamma, you can actually manipulate the distance between distance measure. Okay. Okay. So when you manipulate distance measure, what happens? If you try to create too much distance between one type of class and another type of class, is that overfitting or underfitting? If you create too much distance between one type of data point and other type of data points, in a way you are creating distance, right? Sorry, yeah, distance only. So this is close to 0 means high distance. Close to 1 means low distance. Right? When you are actually trying to clearly distinguish on the train set, what happens? What might happen? What happens? You're trying to
Underfitting.
Overfitting. When you are
Train
actually
set,
trying,
right?
on train set, overfitting will happen, right? You always try to know it, even in life also it happens like that. Like it's like me, right? I also work like that. So I try to clearly distinguish and clearly have everything very organized. Right? If I go to some other place or some relative's home, right, I'll not be comfortable. Right? That is overfitting, right? I made my place very comfortable, but when I generalize, right, when I try to generalize, when I go to some other place, it is always congested for me. However good they are, how many facilities they are providing, it doesn't matter. I'll be uncomfortable only. So that is overfitting. You are trying to make things so perfect on the train set that may actually cause overfitting. So here we are trying to create a clear distinction by taking the gamma a big number, right? That way you may end up with overfitted model. When you end up with overfitted model, you need to reduce this gamma. When you reduce gamma, overfitting reduces. When you increase gamma, overfitting increases. Right? See this here. There is some overlap here, and there is boundary violation. There are data points falling on the wrong side and all that here, right? So there should be a balance. It should not be like the model should not work at all on the train set. Our model should work perfectly on the train set. There should be a balance. Okay. So here, when I reduced the gamma, it actually became a little, here and there. The data points are very close to the, and some data points may have fallen on the wrong side also. So if you see this, right, it is actually raising a new dimension. Kernel is the new dimension. So if you look at it carefully, right, it is calculating distance. That distance is nothing but the third dimension. So whatever distance you are calculating is the third dimension using x1, x2. If you have 100 columns, right, it is going to add 101 columns. So what happened? Basically, the 1 million column data set, you convert it to 5 columns because you have 5 rows. If you have 100 rows, you would have converted into 100 by 100. If you have 1000 rows, 1000 by 1000. The kernel trick is going to be useful only when the number of columns are more than number of rows. Okay, when number of columns are more than number of rows, the data set will reduce the dimensionality or size will reduce. Right, 5 by 1 million became 5 by 5. Right, 1000 by 1 million becomes 1000 by 1000. 10,000 by 1 million becomes 10,000 by 1000. 10,000 by 10,000. More than 50,000 or 1 lakh records, if you try to use kernel SVM, it's going to damage. Because it's going to create, if you have 3 columns and 1000 rows, if you apply kernel trick, right, it will become 1000 by 1000 matrix. Do you agree? You have 3 columns and 1000 rows, right? 1000 rows and 3 columns. I should be saying rows first. 1000 rows and 3 columns. If you apply kernel trick, it becomes 1000 by 1000 matrix. Do you agree?
Yes, sir.
Right? Applying kernel trick on a less number of column data set is completely useless. When the number of columns are more, you are unable to find out pattern well. You want to make the data set intelligent. That time you can use it, and the kernel SVM trick also will not work more than the data sets with more than 1 lakh records. It depends on your memory. If you have 250 GB of RAM, right, you can use maybe 1 million records also. But usually we will not have it, and we no need to have it because we have more powerful techniques like boosting algorithms and the deep learning algorithms. Okay, so basically why am I explaining this? Because there is a concept called as kernel PCA, right? Principal component analysis is another uh, clustering, sorry, the dimensionality reduction algorithm, where you apply this way of converting data, extract intelligence like this using kernel trick, and then apply dimensionality reduction. So there also the same kernel trick will come. That's where I explained SVM here. So any questions?
Yes, sir. Actually, the calculations, they are not correct, sir. Can you please go to that gamma equal to 1 and gamma equal to 0.5? Yeah,
Sure,
this slide. So here, RBF function for gamma equal to 1, denominator should have divided by 2 because it's a 2 gamma, right? Or 2 rho.
No. 1 by 2 sigma square is equal to gamma. They actually engulfed everything into gamma. 1 by 2 gamma sigma square is gamma.
Oh, okay.
They made it simple.
Okay.
Actual
I did
RBF
not
function.
notice.
Yeah, that's fine. Yeah, that's fine. Simple, right? If you take 2 gamma square and you put gamma there and try to divide and all that, it's going to be complex. To explain it simply, I took gamma is equal to 1 and 0.5. Right.
So which is actually the kernel trick? Is it calculating this
RBF,
kernel?
RBF is the kernel trick. This whole thing is kernel trick. This equation is kernel trick. You applied kernel trick, you converted your 5 by 1 million data set into 5 by 5. Okay. Then on this data set, we will apply SVM, that is called as kernel SVM. This is whole thing is a kernel trick only. Whatever we saw here so far is kernel trick. The decision boundary thing, this hyperplane is the SVM.
Hyperplane is the?
SVM, algorithm. Algorithm trying to distinguish data, right now, do decision boundary. The kernel trick actually made this data like this, clearly distinguished, like this or this. When you manipulated data became like this, and then you are applying SVM algorithm that actually is distinguishing data clearly. Got it?
Yes, sir.
Any other questions? So go through the presentation. It'll